Hello students, let's continue with the solved examples related to decimal expansions of real numbers. However, before we proceed further, let's make sure that our concepts are clear. So in the previous class, we had seen divisions of rational and irrational numbers, right? So we observed two things wherein the remainder became 0 and when the remainder never becomes 0, right? So when the remainder becomes 0, those decimals are known as terminating decimals, or those rational numbers would be referred to as terminating decimals. And in the case where the remainder does not become 0, it is referred to as non-terminating and recurring, because there was a repeated pattern that was taking place, right? So here, for example, we have 1 upon 7 as we saw in the previous example. Our quotient was 0.142857, okay, this section. Again, the same pattern repeated, that is 142857, again 142857. So we do not really want to keep writing this until eternity, right? So there is a way to represent this number. I will say 1.7 is equal to 0.142857 bar, okay? Now the bar starts at 1 and ends at 7, which means that all these 6 digits are going to repeat, okay? Which means nothing but 142857 bar is 0.142857, 142857, 142857 and so on. Now you have only one digit repeating here after the decimal, which is 3. So I am going to write this as 0.3 bar, okay? Another example, suppose you have a number like 0.1282828. Now you notice that only this sequence is repeating, 28. So what I will do is I will write 0.128 and a bar only on top of 28, okay? It won't be on top of 1 because 1 is not repeating. We initially got 1 after the decimal, but only 28 is repeating, which is why there is a bar only on 28, which means this is equal to 0.1282828 and so on. Right. So now since we are clear about these concepts, let's go ahead and take a look at the solved example on page 11. Show that 3.14268 is a rational number. In other words, express 3.14268 in the form of P upon Q, where P and Q are integers. Now see, Z is always denoted as, Z stands for integers, right? So why am I not, see, natural numbers we denote as N, whole numbers we denote with W, real numbers are denoted by R, right? Then why integers are not represented by I? Because the word integers is derived from the word zehleen, which means to count, right? So in the number line, we count from the negative infinity side to the positive infinity side, right? That is why integers are represented as Z, okay? So this was just a pointer that I missed out to mention earlier, which is why it just occurred to me and I mentioned it to you. So anyway, where P and Q are integers and Q is not equal to 0. Now this is the definition of our rational numbers and we need to represent this in the similar form. So I'll say my solution is, my number is 3.14268, right? Now how many places after the decimal? Let's count. 1, 2, 3, 4 and 5, right? So this can be represented as 31468 upon 5 numbers that we counted after the decimal. So I'll add 5 zeros here. 1, 2, 3, 4, 5. Of course, we have learned this in our 8th grade, right? Whenever you want to remove the decimal, you count the number of digits after the decimal and add those many number of zeros after a 1 in the denominator, okay? So this is represented in the form of P upon Q, right? Where 314268 is an integer and 100000 is also an integer, okay? And Q is not equal to 0. Therefore, we have solved this sum, okay? Now let's go ahead and solve the next solved example. So my next solved example is number 7, which is on page 11 itself. Let me quickly write that down. Okay, so I need to show that 0.3333, which is equal to 0.3 bar, can be expressed in the form of P upon Q, where P and Q are integers and Q is not equal to 0. So in short, we need to show that 0.3 bar is a rational number, right? Now we saw in the previous example, we had a number, I do not remember, but it was something similar to 0.31246, okay? I do not remember the exact number of digits. So here expressing it was easy in the form of a rational number, where I just removed the number of 0, I just removed the decimal place and added those many zeros after a 1 in the denominator. This was 31246 upon 12345, right? Now what is the difference between this number and this number? Here we have 3 repeating itself. So we do not know until when it is repeating, because it is repeating until infinity. So we cannot write 0.333333 and so on as 3 upon. This is a wrong denotation, right? So let's see how we are going to solve it. I'm going to give 0.3333 a name, okay? So I'll say solution. Let x be equal to 0.3333 and so on, right? Now we have only one digit repeating after the decimal. So what I'm going to do is multiply both the left hand and the right hand side with 10. Why 10? Just because one number is repeating, so I multiply with 10. If there were two numbers repeating, I would multiply it by 100 and so on. Okay, so I'll say multiplying both sides by 10. What do we get? 10x is equal to 1.33, hang on, 3.3333 and so on, right? Now see how I split my 3.333 in order to write this number in the form of a rational number. 3.33 can be written as 3 plus 0.3333. Okay, so if you're getting confused that there are 4 3's here and why did I write 4 3's after a decimal, let's remove it, no need. So I have 3 numbers over here, okay? Okay, so anyway, this can be n number of 3's over here, there can be n number of 3's over here. Now this is nothing but what? It's my x. Let's say I add another 3. So this is 3 plus x, right? I have 10x on my left hand side. Now I have x here and 10x here, so what I will do is I'll bring x on my left hand side. Since it is holding a positive sign here, it will come here and become negative, right? Because it's moving from one side to the other of the equal to sign. So I will have 10x minus x is equal to 3, right? Therefore 10x minus x is nothing but 10 apples minus 1 apple, right? This is 1x or x. So 9x is equal to 3, right? So 9 is getting multiplied with x over here. It will come on this side of my equal to sign and it will divide. So I get x is equal to 3 upon 9. Now I can simply cancel. 3 1's are 3, 3 3's are 9. So you see that x is equal to 1 upon 3. But what was my x? My x was 0.333 or 0.3 mod. So 0.333 or equal to 0.3 bar, right? So you see that I have represented my 0.3 bar in the form of P upon Q, where P and Q, that is 1 and 3, both are integers, and Q, which is 3, is not equal to 0. Please take a look. So let us go ahead and solve the next question of our solved examples. I will quickly write the sum for out. This is similar to my previous solved example, that was 7. We are on the 8th one, where we need to show that 1.272727, which is equal to 1.27 bar, can be expressed in the form of P upon Q, where P and Q are integers and Q is not equal to 0. So let us go ahead and find the solution. Like we did the previous example, I'll say let x be equal to this number. So let x be equal to 1.272727 and so on. Okay. Now see how many numbers are repeating. There are 2 numbers that are repeating, right? 2, 7 is being repeated, that makes it 2. So I'm going to multiply the left hand side and the right hand side with 100. So multiplying both sides by 100. What do I get? 100x is equal to 127.2727 and so on. Now see, here is the catch. We need to split 127.272727 in such a way that we get plus x on the left hand side, on the right hand side. So how am I going to do that? Let's see. I have 127.777. Now what do I need? 0.272727. Okay. So I need 1.27. What if I subtract 1.27 from this? I get 126 plus 1.272727 and so on, right? So this number will become x, right? So let me write 127.272727 as 126 plus 1.2727 and so on, right? See, 126 plus 1.2727 is going to give me 127.2727 and so on, right? So this is equal to 126 plus x, right? So if you notice in this entire sum, only finding this out, these 2 terms is the trick. Once you have it, once you have split the term that we have over here, then solving the rest of the sum becomes very easy. I'm going to bring my x on my left hand side. So what do I get? 100 my x minus x, which is similar to 100 apples minus 1 apple, okay, is equal to 126, right? So what do I get? 99x is equal to 126, right? Now x is getting multiplied with 99, so 99 will come here and divide 126. So x is equal to 126 upon 99. Let's see if we can cancel these further. I have 99, which will go in 3, and 126. When you add 6, 2 and 1, what do I get? 9. So 9 is also a multiple of 3. So let's cancel. 3 3s are 9, 3 3s are 9, 3 4s are 12, 3 2s are 6. Okay. Then I have 3 11s are 33, 3 1s are 3, 3 4s are 12. So what do I get? 14 upon 11, which is my x. X is nothing but equal to 1.27 bar. Therefore, I have represented 1.27 in the form of P upon Q, where P and Q are integers, 14 and 11 are integers, and Q is not equal to 0, right? 11 is not equal to 0. Therefore, we have solved this example. We will continue with the rest of the solved examples in the next class. Thank you.
Hope this video increased your knowledge. For more such videos and a completely free educational content, log on to www.epathshala.org or visit our ePathshala YouTube channel. We have each and every question solved for maths, physics, chemistry and biology. So subscribe our channel, share with your friends, like our Facebook page and follow our Twitter handle for regular updates and important educational tips, and also win ePathshala goodies. So what are you waiting for? Subscribe this channel and enjoy the freedom of education.